Just a little bit. Boudart Award was started in 2007, and of course, the recipient for this year. Only 3 awards given so far, starting with Alex Bell, who's here, and Evelina Corman, followed by Jim Domestic, who would be the one introducing the speaker. The next slide. So the award was started with Alex Bell, with a nice photograph of the two in Houston. And I vividly remember being there and enjoying the very first award. So the award is given, as you can see there, in recognition of individual contributions to the elucidation of the mechanisms and active sites involved in catalytic phenomena, and the development of new methods and concepts that advance the understanding and/or practice of heterogeneous catalysis. The first award recipient, as I mentioned, was Alex Bell, and now I'll call upon Jim to do the introduction of the current recipient. Thank you.
Yeah, could I have the next slide, please? So it's my pleasure to have this opportunity to introduce Jens for the Boudart Award. I put on my first slide some biographical information that you can read along as I just walk you through it. His master's and PhD from the University of Aarhus, postdoc at the IBM Watson Research Center. He then entered employment in Boudart, spent a brief time at the Nordic Institute for Theoretical Physics as an assistant professor, and then moved to the VTU, where he spent the majority of his career. During that time, of course, he kept his strong ties with Boudart. And recently, within the last 2 years, has moved to the U.S. at Stanford and SLAC. Over 400 publications and an astronomical H factor. Too many awards to list. I've given a couple recent ones: the Ritash Award, the Aerial Lecture Award, and the Summertime Award. The next slide, please. This is, I tried to encapsulate after discussion with Manos Mavrakakis, some of the highlights maybe of his accomplishments over the last few years, developing molecular level descriptions of mechanisms and surface sites, introduced the standard model for transition level reactivity with the Advanced Center, a strong proponent in the quantification of the Bronsted-Evans-Polanyi relationships, extensive work, obviously, in computational methods to describe reactivity, pioneered catalyst design concepts, aka microkinetics, and recently has introduced some database for surface chemical properties and software. And the last one really comes, if you look on the web page of the North American Catalysis Society, there's a bio on Boudart that Fabio, Nick, Henrik, and Enrique put together. And near the end, you'll see this statement or adage of Boudart, which I think typifies Jens's approach. And that is, do not lament what you don't know, make the most of what you do know. And in the final slide, could you please move to it? Just a brief statement about Jens Norskov, the person. I think most of us in this audience have had the great pleasure to get to know Jens over the years. And I think we all would agree, besides being a world-class theorist, he's a person who works enormously closely with experimentalists, including surface scientists as well as catalytic practitioners. He's mentored countless researchers. I count myself among his mentorees in the so-called Norskov school. He doesn't say that, but maybe we say that. And someone who strives to bridge the gap between theory, surface science, heterogeneous catalysis. And please now, take off your ties, get ready, in search of the catalyst genome.
very nice introduction. Thank you also to the North American Catalysis Society and the European counterpart for the award. I'm deeply honored. I have been very influenced by Michel Boudart during my upbringing as a scientist, and I'm very proud to have an award named after him. I'm sorry you couldn't be here this year, the first time, but I think you would have liked the approach that I'll be describing here. That's the way he was thinking. Now, finally, let me thank all of those who actually got up very early this morning and sitting here. So that's heartwarming. I'll move on directly and talk about what I will be talking about. Now, the catalyst genome. For the purposes of this talk, this is simply the set of instructions that define the catalytic properties of a given material. Now, of course, if we have the structure and composition of the catalyst, we know, or at least we can go and make the experiment, and we know what the catalytic properties are. But that doesn't help us much, because most people would not be able to, for instance, predict that molybdenum disulfide, shown in the slide here, should be a good electrocatalyst for hydrogen evolution. So we need more information, or better information, information that can take us directly towards the catalytic properties, not just structure. Now, in principle, the link between the structure and the functionality of the material is the electronic structure. All the information about the functionality is in the electronic structure. But again, that's an almost empty statement. Most people cannot look at a band structure like the one shown here from molybdenum disulfide and say this is a good hydrogen evolution catalyst. We need ways of distilling out the most important parameters that describe this. And that's what I'll be talking about today, or at least some feeble attempts at doing that. If we could do that, and if we could have this information stored for everybody to be able to access, from experimental data, from computational data, from theory, if we had databases of properties determining catalytic activity, we would have a fantastic design tool for new catalysts. So that's the long-term goal for the kind of things that I'm talking about. And this is what I'll talk about today as well. Now, this whole question of searching for the instructions determining catalytic activities, that's of course something that is as old as the field of heterogeneous catalysis itself. There's always been searches for links between, say, structure and functionality, or spectroscopy and functionality, and so on. I'm just showing a couple of examples here. One that's about 30 years old from the Tosser group, correlating the activity for hydrogen desulfurization with a particular structure of cobalt sitting in the edge of a molybdenum disulfide particle. Or a very new one here from the group of Brasilians and Schwebe in Berlin, correlating the activity for methanol synthesis with the existence of a particular kind of stachyphores in the catalyst. The problem with these things, they're very important for this particular system, but it's very hard to generalize. How do we do this for another kind of system? So, what's new? And there are actually several very important new developments in the field of heterogeneous catalysis. The one that I'll focus on here, simply because it's the one that I know about, is the new developments in theory. We are beginning to have a predictive power in theory, and that gives us completely new possibilities for insights into what is important and not important for heterogeneous catalysis. The first example I'm showing here is one from actually Kim Domestic's group and the group of Markakis comparing theory and experiment the external frequencies as a function of various properties. Not so important here for ethylene glycol reforming. What you should notice here is theory and experiment in terms of the variation with these parameters agree extremely well. That's predictability. Another example I will show here, because I'll get back to it later, is this one here. This is a comparison of a model based on the electronic structure calculations of the rate of hydrogen evolution, electrocatalytic hydrogen evolution, and compared to experimental data collected by Ulrich Stimming from a very large number of groups. And you can see here that sort of general order of magnitude comes out well, but much more importantly, the variations, the trends from one catalyst to the next also come out. That's the other kind of predictive theory that is very, very important here, perhaps even more important than the actual magnitude. So, what I'll be talking about today is how we link between the data, the activation energies, the bond energies, and the catalytic properties. We can of course try to just move directly from one to the other, but as I talked about earlier, this is very, very cumbersome. You don't gain any insight, and you don't have anything that you can generalize to the next system. What we need is a set of data about the data. We need models, and we need to be able to distill out the descriptors that determine catalytic activity. The most important ones. Obviously, if you want all the details, you have to do the full system. But if you want to get an overview of what is a good catalyst and what is not, then you need to distill out and you have to have confidence that you can do it at a certain level of understanding. And then if you want all the details, then you go to the next level. That's the approach here. So what I'll do is I'll say a little bit about how electronic structure methods work today in terms of their accuracy, and then I'll move directly on to this question of distilling out descriptors of catalytic activity, and I'll take you through 3 examples. First, there are simple ones, actually 2 very simple ones, the hydrogen evolution reaction and ammonia synthesis, and then I'll move on to larger and larger complexity. First, talk about syntax reactions, including not just activity, but selectivity, and then move on to large-scale material screening for photochemical water split. And then I'll return to the question of what are the underlying electronic factors that determine this, and at the end also about data access and management. So that's the outline. So first a little bit about electronic structure methods. This is a comparison of benchmarking, if you like, of various electronic structure methods as we use them today against very good calculations for small systems. The G2 database shown here, that's a database of very accurate chemical calculations for small molecules that we can use as a benchmark. The S22 database is a similar high-quality database for weakly bound systems. And then for chemosorption, there we don't have any high-quality calculations as yet. And there we are taking the best we can find in terms of experiments. And you can see some of the contributors to the experimental data that we're using to benchmark our methods. And what you see is that there are, if you look at the what is it, purple PBE column there, what's shown there is the mean absolute error, MAE, mean absolute error for this set of calculations. And PBE is very popular in solid-state physics because it actually describes solids quite well. You can see it describes molecules and absorption on surfaces quite poorly. That doesn't mean you can't get trends right, but it certainly means that absolute magnitudes are not very well described. If you go to something like B3 lib, the red bar, that is very good but we can only use it for small molecule for molecular systems unless you do expressions to it. And the other two that are included is RPD, which we've been using a lot, and many people are using a lot. It's actually very good for absorption systems. We have errors of the order of 0.1 eV, 10 kilojoules per mole. And we have a new functional that includes van der Waals interactions, that's the blue, and that actually is a very good all-round function. To give you an idea what it means, let me benchmark this a little. To the left here, what you see is a comparison of theory and experiment for oxygen adsorption energies on all the 4D transition metals. Comparison to an experimental combination or sonograph. And what you see is that there is actually a very good description of variations. Another set of trends that come out quite well is shown to the right. Here you have experimental data for the oxygen adsorption of platinum 111 as a function of coverage. And the red is the theory, and again, absolute magnitude and the variations actually come out very well. I think the fact that the bond strength decreases faster than experiment than theory is actually the equilibrium structure, and the experiment may not exactly have the equilibrium structure in the way they are done in the group of the shocking camp. But I think, again, it gives a lot of confidence in what we can do at this point in time. Just one word about the possibilities that are coming now that we can begin to describe dispersion of the interactions at the same level as we described the consortium. It's not an add-on, it's really at the same level. This is a comparison of theory and experiment, calculations by Boudart, looking at alkanes, it says NAM23. You can see if you do this at the RPD level, you get only the repulsion as the alkane gets longer and longer. If we include the van der Waals interaction, we actually describe the variation observed experimentally very well. So this opens up a totally new set of areas of heterogeneous technologies that we can describe at this level of the theory as well. So let me move on to the question of identifying descriptors. And let's go back to the hydrogen evolution volcano. How's that done? So this is a free energy diagram for hydrogen evolution. You start with protons and electrons. 2 times you adsorb that. Then you have adsorbed hydrogen, or 2 adsorbed hydrogen, and then you desorb the hydrogen as H2. This is one of the several mechanisms we looked at. I don't want to go into the details here. It's shown here at 3 different potentials. At a positive potential where it's uphill, and at a negative potential where it's downhill. The important thing to notice here, the only important thing to notice here is that there's one way to determine this. There's one area that's much higher than the rest, and that's the desorption of hydrogen. That means that we can write the rate in this manner here. You need 2 hydrogens, so there's a theta hydrogen squared in the rate expression, and then since we include interactions with all neighbors in this model here, we have a sum over all possible configurations of the hydrogen that desorbs, and then the probability of having that configuration and a rate constant for that particular configuration. Excavation area depends on coverage. And we can do Monte Carlo simulation for these probabilities, that's also important here. The important thing to notice is that when we plot the activation area and plot it as a function of the reaction energy, that is the hydrogen adsorption energy, there's a nice linear relationship, both as a function of the potential and as a function of matter. What that means is the following. There are only 2 parameters that characterize the catalyst here, theta and the rate constant K. Now, theta obviously depends on the hydrogen adsorption energy only. And K depends on the activation energy, which you can see is a linear function of the hydrogen adsorption energy. That means there's only one variable in the problem that characterizes the catalyst. This is the model that was solved to get this. And so this is a and of course, the usual explanation here on the left side, you bind hydrogen too strongly. In fact, for the dashed, you don't even, they actually oxidize. They're outside reach anyhow. But on the left side of the volcano, the hydrogen desorption is slow, and on the right side, there's no hydrogen on the surface. The point here is that we have a description on it. The free energy of hydrogen absorption describes it. Now, there's been volcanoes like this have been known for 60 years or so in this field, as in ordinary heterogeneous analysis. The important thing in this context is that now we know what to put on the x-axis in detail. We know now that the free energy of hydrogen absorption should be close to zero, and that gives us a design tool. Because obviously, if we can find other materials with the free energy of hydrogen absorption close to zero, then they should also be a good catalyst. I would have predicted power if it works. So let's test it, and we certainly, and by we I mean Jeff Greeley, made a very large number of calculations, hundreds of hydrogen absorption energies, plotted here so that each dot is an alloy, and you have activity is best as you go to the left, delta G close to zero, and included here is also the stability of the alloy, because obviously you want something stable. And so you need to be down in the lower left corner, and you'll notice that's where there are fewest points. It's always like that. What's even worse, if you look at the best compromise between stability and activity, you've got platinum, and then a number of platinum and rhodium alloys. It looks as if this with platinum should be better, and in fact it is. Tom Camillo and Ipokenov did experiments to actually show that that's the case, but it's not really very useful, right? So what we did was we said, well, let's go to other classes of materials, and that's a freedom we have, since this is something we can do on the computer. And this is where molybdenum disulfide comes in, because we had a lot of calculations of molybdenum disulfide there already, so we just have to pull it out of the computer. It turns out if you bind hydrogen at the edge of molybdenum disulfide, then it has a binding energy pretty close to zero. So we again persuaded our friends Ipokenov and Tom Camillo to do some experiments that put molybdenum disulfide nanoparticles on the goals support. Nanoparticles because you want a lot of free exercise. And they found a pretty decent activity. I wasn't totally happy with the fact that it's sort of lingering below where it ought to be. So recently, Charles Tsai and Frank Peters, they've done calculations looking what is actually the effect of the gold substrate. There is one. In fact, it should be here. So there's still the hope that intrinsically the molysulfide is actually quite a bit better, and there are some very recent experiments in the group with Gistray also at Stanford, where they can now make molysulfide stand up on a support so that it exposes only edges in a very controlled manner. And that actually looks quite a bit better. In fact, you can take this and make a device out of it. So this was done in the group of Copenhagen again. So this black dot that you see in the middle there, that's actually silicon balls. And they're there to absorb the infrared part of the solar spectrum to give you the electrons that will react with the protons to make hydrogen. Then you put molysulfide on top of there, and then you shine infrared light on it, and you'll see that here in a moment. You'll see light coming on there, and now I hope you can see the hydrogen bubbling up. So you can actually now make a device based not on platinum or anything expensive that can easily keep up with the flux of solar photons in to make hydrogen. for that part is actually one that we can say we have solutions now. If you want to look at the data they're here, but the important thing is that without any bias or anything, we'll have a very healthy rate of hydrogen evolution based on a device like this. In fact, in some Javier's group, they're refining the catalyst side more and more, making more and more nanoporous materials, exposing more and more S-sites, and you can see down in the lower right corner that shows all potential as a function of current density or water current density. Down to the right, lower right, you have the noble metals, and you have the non-noble metals up to the left, and you can see that the molybdenum sulfide is slowly approaching the noble metals in terms of activity per surface area, and we're within an order of magnitude now of that and similar materials. Now let's try and become a little bit more complex, and let's look at ammonia synthesis. Here's the calculated potential energy diagram for each step. Not so important. The important thing is that there are 7 steps. There are 14 activation areas in this problem. 7 forward and 7 backwards. So if we wanted to optimize this, we would have a 14-dimensional optimization problem. That's very, very hard. It's very hard to develop any intuition about what to do. But thankfully, the problem can be reduced. And here's the way to do that. It's just like what you saw for the hydrogen evolution, that there was a relationship between the barrier for hydrogen evolution and the hydrogen absorption energy. Here it's the same. These are plots of the binding energies of nitrogen, hydrogen X, where X is 1 or 2, as a function of the binding energy of nitrogen on a number of different metals. Red is a step, black is a flat surface, only the steps matter. You can see that here, where you see the barrier for instant dissociation at the steps is much, much lower than on the surface. Now, this already reduces the dimensionality by 2, right? If you know the nitrogen binding energy, you also know the NH and the NH2 binding energy. This is a relationship between, again, calculations on a number of different metals and a number of different structures, the relationship between activation energy for instant dissociation and, again, the dissociative absorption energy of nitrogen. There's a nice monatomic, well-defined relationship between the two, further reduction in dimensionality. And here are scaling relations for all kinds of hydrogenation reactions, and that reduces the dimensionality again. Now, the end result is that if you know the nitrogen and the hydrogen binding energy, you have the first guess at all the barriers in the problem. Now, the hydrogen binding energy varies much, much less than the nitrogen binding energy from one system to the next. So effectively, we have a one-dimensional problem. And here's actually a neat field kinetic model of ammonia synthesis based on the calculations that I showed you. This is rate, or turnover frequency, for the active site as a function of the nitrogen dissociative absorption energy. You see a very nice volcano with a maximum quite close to ruthenium. We added here, this is Alexander Horkovich and Felix Stuck in particular done on this, added the effect of Passion promotion to get closer to experiment, which is shown on here, and you see that's actually a very good relationship. What it means is that we have a parameter, we have a descriptor for good activity for ammonia synthesis. Now, let's move on. That was simple. Let's look at syngas reactions. So let's look at reactions where hydrogen, and first I'll talk just about hydrogen and carbon monoxide, making a number of different products. And now we are talking not just about rate, but also about selectivity. Which product will a certain catalyst make? Will it make methane or higher hydrocarbons? Will it make alcohols, ethanol? What will it do? And so this is a very demanding problem. If you include just step size, the most active, you include methylation, you include methanol synthesis, and just ethanol, the C2 alcohol, and nothing more. Then there are 51 elementary steps. That means 102 parameters, activation energies, one way and the other way. So we are now up to 102 parameters optimization space. Very, very difficult if you don't have simplifications. And in this work, done in particular by A.J. Method and Adam Lauscher, what they did was they simply established scaling relations for all of these different elementary steps. It looks like a lot of work. It was a lot of work. But of course, this can be used for another reaction as well. I mean, it's not work that you have to redo for each new reaction. Any reaction that involves, say, the CO1 splitting of the methoxy, you can use this data as well. Those data that are there in databases for everybody to use. Now, if you do that, then again you reduce the problem so that basically you need to know the carbon binding energy and the oxygen binding energy, and you have a first approximation, let me stress that, to what determines the rate. So here is a solution of the microkinetic model as a function of those two parameters. So each metal here is characterized by those two parameters. You can see each metal put on here. This is the rate of methane production. You also see each metal has sort of an uncertainty bar. That's simply to indicate if we have an uncertainty in our calculated absorption energy of carbon of plus minus 0.2 eV, what does it mean here? And you can see that errors of that order of magnitude does not affect any conclusions that we can make on the basis of this. You see a good healthy maximum where it should be ruthenium, rhodium, nickel. They are known to be the best methylation factors. That's what you would expect. You also see there's another interesting maximum over to the right for weak and carbon binding energies. That came as a surprise to us. We have been doing calculations, I'll show you that in a moment, but we only look at the direct CO2 association or hydrogen-assisted CO2 association. Since in this model we also have methanol synthesis, then we also go all the way to have methoxy, for instance, and that actually comes from making methoxy and then breaking the CO1 after making methoxy. So that's a secondary maximum there. But this describes quite well what we know in terms of the activity of various methods for methylation. I'll just say one word here on the effect of assorted interactions. Certainly when you have strong binding of oxygen and carbon, that is something you need to include. And we've done that here. This is a model by Adam Lauscher and trying to have Peterson and Scoop, where they have did methylation but did not include this methoxy species, so it's different. The reaction conditions here are also very different from what I showed you before. So the left plot would be identical to what I showed you before, that the reaction conditions were in the same. Now, the left one being no interactions to the right, we include assorted interactions in a very elaborate model. And what you can see is that around the maximum, absolutely nothing happens. The point is the maximum basically is defined as where you transition from high coverage to low coverage. That always defined. You can actually show that that coverage is about 1/2. So to the left, stronger bonding side, then there are big effects. You see, rhenium is a very, very lousy factor to the left, but gets much better when you go to the right. That's simply because if you bind carbon and oxygen too strongly, then the assorted interactions repel that, and then you lift it up. And that's actually what you see experimentally as well. So yes, if you want to have the details on the strong binding side, you definitely have to include these effects. Around the maximum, less so. But this is just it does mean, of course, that if you want to look at selectivity, you should function. synthesis, then you do need to include this, definitely. There's no way around it. Okay, getting back to the full model, but now no interactions. Methanol synthesis, copper is certainly close to the maximum, as you would expect, and adding zinc will take it down into the lead, because zinc gives you a stronger oxygen binding energy, so that's what's low. It looks as if nickel and iridium and what have you also have some activity, and they do, but they have much higher methanation activity. So this is really a very minority effect over there. If you look at something like ethanol, then you see that has a nice maximum, but unfortunately in the middle of a complete desert in terms of the metals. And you can combine now all three, and then you can get selectivity maps. So this is now the blue is the selectivity for methane, green for methanol, and red for ethanol. And you can see that you have the weak binding, you have all methanol, the strong binding, you have all hydrocarbons, and then you have this sliver of the phase space where you might be able to make high alcohols. And I think this explains very nicely why there is no commercial high alcohol catalyst at the moment. It's very, very hard to find. The question is, of course, what can we do in terms of alloying and other tricks to move into this area? And that's where we are at the moment, investigating that. But I think the insight that you get in terms of understanding the mapping of activity and selectivity onto various descriptors comes out very nicely in a form like this. Let me just show you an example where we have taken it one step further in terms of getting to the question of the new catalyst. So you saw here making hydrogen, we can do that. If you want, let's assume you have sort of a small scale activity where you can make hydrogen. How would you make use of that? Of course, it would be nice if you could reduce CO2 directly electrochemically. That would be more photoelectric. That would be wonderful. But let's leave that aside. There were several talks about that yesterday. But you could also be active with CO2. But if you have a small hydrogen production, you also want a small, low-pressure reactor for this. You can't use the common large-scale, high-pressure process. So let's see if we could find something that would be kind enough to work at low pressures to do this. It turns out that if you reduce CO2 only, then, as Alex Bell has also observed 10 years ago, or 15, most of them only include the oxygen. And so you can actually make a volcano just as a constant oxygen binding energy. And this is the volcano you get out. And you can see copper there. You can add zinc, or actually other oxophilic materials. And again, Alex Bell has been pioneering that many years ago, or several years ago, I should say. But we thought, let's look at something else. And we found that nickel gallium alloys actually look quite interesting. So here are experiments now in the group of the Copenhagen again, and if you look at the upper right, that is the rate. I could have shown turnover frequencies. It's the same. The particle sizes are basically the same for these different as for copper. We've shown there are different alloys of nickel and gallium, and compared to the commercial, or something close to the commercial, zinc oxide promoted copper catalyst. And you see that's the yellow, right? So what you see is actually that several of these get quite a bit better at high temperatures. The reason is the following, and that's actually even more important. If you look below, then you see how much CO comes out. The copper catalyst actually runs the reverse order and shift reaction, the second reaction shown in the upper right corner, very efficient. So it makes a lot of carbon monoxide. If you only have hydrogen and CO2, you will make a lot of carbon monoxide. That rate is reduced by a factor of 10 for the nickel gallium. So this is actually a catalyst that will make only a little bit of carbon monoxide and a lot of methanol in water. That's actually a very, very attractive way of making methanol in a small-scale process like this. So this is another example of where we can get to at least new ideas. This doesn't make a catalyst, but new ideas for catalysts and processes by knowing enough about what's important and not important for the reactivity. That brings me to the last example. Let's say we wanted to split water, and what we need there is a semiconductor that has a band gap so that the electrons are good enough to make hydrogen, and the holes have high enough energy to split the water and make oxygen, and the protons you need to make hydrogen. So there are three requirements. We need a semiconductor with the right band gap and band edges. We need a catalyst that can split water, and we need a fuel production hydrogen evolution catalyst. That's the blue one. We know one that we could use for the blue. That's the polysulfide I showed you. There is a lot of interest right now in finding the green catalyst. But of course, the dream would be, could we find one material that could do it all? As Tom Camillo has shown in this cartoon here, if we had such a catalyst, all you needed was to take a powder of this and put it into water and put it in a plastic bag and then put it out in the field or the ocean, and you would make hydrogen and oxygen. You might have to worry a little bit about the explosion, but that's all you needed. If we had this one material that could do it all. So, does it exist? Well, I'm not going to answer yes or no to that question. But we looked around. It started with a work by Carsten Jacobsen and Christian Thuesen at the Technical University of Denmark, where they looked for band gaps for a large number of cubic perovskites of the composition shown here, one metal, another metal, oxygen 3 - X, nitrogen X. And in each case, they made a selection. They wanted the band gaps to be in the range 1.5 to 3 eV. It needs to be more than 1.5, otherwise you can't split water. Less than 3 to have a reasonable efficiency. The other is that it should have a reasonable stability. And the final is that it should have band edges that lines up with the hydrogen evolution and the oxygen evolution potentials. And what is shown over there is a screening just of two of the parameters. A band gap should be in the red region. That's the upper right triangle in each of these squares. And the helium formation should also be in the red. And you can see already now that there are incredibly few red squares. Right? In fact, if you then include the band alignment, it turns out that out of about 20,000 different materials that they screened, theoretically, there are about 15 that have band edges that line up nicely with respect to hydrogen evolution and oxygen evolution. So that's an enormous reduction in the number of systems that you might want to consider. The next step is, of course, can these make hydrogen and can these split water? And there, Jordan Montoya and Alexander Boudart have done calculations now of the overall potential for hydrogen evolution and for oxygen evolution. The hydrogen evolution overall potential is shown here in blue and the oxygen in green. And what you see is that out of the 15 potential candidates, there are extremely few left. In fact, so on a good day, probably platinum titanium oxynitride. And that's actually one that has been tested and looks quite reasonable in the group of the Genome in Tokyo. So I think the answer to the question I posed, how is this, can we find one material, is probably, it's going to be very difficult. I don't want to exclude anything. I mean, we just look at one class of materials in one structure, but it's probably very difficult. So we may need to have a several component particle particles to throw into these plastic bags that we want to use. Okay, let's say just a few words about electronic structure descriptors. What has been very useful to us at least is to think of the bonding of something like oxygen or nitrogen or carbon or whatever it is that determines the reactivity to a transition metal in terms of first a coupling to the sp electrons and then an additional coupling to the ds. And it turns out that most of the fragments, most of the variations in bond energy from one system to the next come from the interaction with the ds. That's not entirely true, and that's I point here to a very recent review by Susan Minnick, where it discusses this, but also discuss the exceptions to these rules, and the exceptions that are related to a large extent to the fact that the coupling to the sp electrons cannot always be assumed to be constant. But for most systems, knowing where the d electrons are in energy is a good indicator. Obviously, there are a number of parameters that describe this. The coupling matrix element obviously is important. Where are the d states is important, and where are the adsorbate states is important. But if we compare the same adsorbate, the same transition state or final state, over different catalysts, then of course FRA is the same. If we use catalysts that have roughly the same coupling matrix element, then it's only where are the d states that is important for the strength of the bonding. And you show that it's shown here for the 4D metals that have often the same bond energy, coupling matrix element, that the trends, the variation in bond energy is given by the variation in where are the d states. The higher in energy the d states, the more reactive the metal. Now this is actually better described in terms of when you have one metal and you then alloy it, and these are calculations by John Kitchen quite a few years back, looking at how 3D metals can shift the d states of the platinum quite substantially and can shift the oxygen, hydrogen, and other metal bond energies equally substantially. And that's something that we're using constantly in experiments. You can see this in experiments. These are experiments by Sasa and Wilson. You see to the left, in the upper curve, you see pure platinum and platinum with copper. And you see how adding the copper shifts the d states down in energy. And at the same time, you see that to the right. Whereas pure platinum has some antibonding states above the Fermi level. When you go to platinum on copper, then you see the antibonding states shift below the Fermi level, and you get a weaker bonding. This is exactly experimental confirmation of this picture. This gives us some insight into where these scaling relations come from. So here is the energy of the metal as a function of the feedback center. Here's the activation area for methane. And obviously, since each depend linearly, roughly linearly on some parameter that describes the electronic structure, if you put one against the other, they also have a linear relationship. So this is the origin of all of these linear relationships or monotonic relationships that I've been showing you that we use to reduce complexity in the model. Finally, let me just say a few words about what we could do if we had all these data, all these descriptors. And the first thing, and we're doing that now, we are collecting that. We invite everybody to submit that data. You can go to the website. And we also provide software you can access it. So you can download here, you go to the website, you can download on any web browser you have, you can access the data that are uploaded by now from several groups, mostly from us. And get out the activation areas of the action energies that are there for your favorite elementary reaction on your favorite metal, only metals at this point. It really means that you don't do a lot of things over and over. At least you check here before you do a calculation. It means that we can now all make correlations. We can find correlations in data that we're interested in. It means we can do data mining. And generally, it just means that everybody can sit down now with their computer or their laptop or their tablet and search around and check good ideas. So that's the basic idea in this. So let me summarize quickly here. We have, I've been discussing finding descriptors of activity and that we need this intermediate level of modeling in order to get a useful take on what is important and not important. Scaling relations are incredibly important because that is what gives you in the end these selectivity and activity maps that I've been talking about. Databases are essential in this context. And this eventually can lead to design strategies, as I've indicated for a couple of very, very simple examples. There are many challenges ahead that I won't have time to talk about here following Jim's advice. But I think the main thing is that to attack these challenges, what we need to do is we need to combine theory, making catalysts, characterizing them, and demonstrating how they work in a concerted fashion. And what links all of this together in the end are the data that we will be collecting doing this. That's the catalyst gene. So let me immediately go and thank this is the current theory group at the Stanford. And I have been showing results from a number of these students and postdocs and staff scientists. I won't have time to go into that now, but I think I mentioned it along the way. Collaborations with a number of experimental groups. And I also show data from a number of students that are now postdocs elsewhere in the world. And with this, I would like to thank you for your attention. Thank you very much.